Good afternoon to all of you. Today we are going to talk about three-phase transformer connections and phasor group. So basically what we have seen, we can have three-phase transformer in a single unit, or it can be constructed using three single-phase transformer. So it will be called as three-phase transformer bank. So these three-phase transformer will be having three primaries and three secondary. So these set of windings are going to represent the three windings. So these windings can be connected in certain fashion. Those fashion could be star connection, it can be delta connection, or it can connected in zigzag fashion. So this particular zigzag fashion, that is called as interconnected star or inter-star. So basically the choice of this connection in which the transformer winding should be connected or can be connected, that will entirely depends upon the service condition, basically where it is going to be placed. So on that basis you can connect three-phase transformer in star, delta, or in inter-star fashion or zigzag connection. So you will have a different types of transformer. If primary is connected in delta, secondary is also connected in delta, so you will call it as delta-delta transformer. Primary, it can be connected in delta, secondary it can connected in star, so it will be delta-star transformer. Primary is connected in star, secondary or second set of windings basically we are talking about, that is connected in delta, so it will star delta. Star-star configuration, that is indicating one set of winding, or primary is connected in star as well as the secondary is also connected in star, so it will be star-star winding. Interconnected star, if primary is connected in that fashion, so it will be called as interconnected star. The secondary, that will be in delta, so it will be your zigzag delta transformer. Primary, it can be connected in again interconnected star, secondary could be star. So these are the configuration you will find out depending upon the connection on which primary and secondary is basically connected. Before proceeding, let us talk about terminals of three-phase transformer. So basically in three-phase transformer there will be three windings on primary, three windings on secondary side, or you can call it as low voltage windings and high voltage winding. So the terminals which you are going to brought out, that will be called as LV terminals. Suppose it is brought out for LV winding, so we will call it as LV terminals. The terminals for HV winding, that will be called as HV terminal. So when you will see practically transformer, so this notation would be there basically. So if suppose there is a small letters, so this small letter is going to indicate LV terminals. A, B, C, it could be, for example, you can consider if it is written A, B, C, so it is going to indicate LV terminals. The HV terminals, that will be usually marked with capital letters. Capital A, capital B, capital C, capital N, that is indicating, N is indicating here neutral. And the three letters, they are indicating three windings. Do not write fourth letter or fifth letter, that is A, B, C, D. So D will not come there because there are only three windings. So three terminals you are going to dot out. So it will be A, B, C, N, that stands for neutral. If suppose there is tertiary winding in a transformer, so that will be that will start with letter the number 3 basically, 3A, that will indicate tertiary winding, 3B, 3C. So basically 3A, 3B, 3C, it is indicating three phases of windings. how the terminal, this letters would be written on terminals basically. So terminals are lettered alphabetically from left to right. From left to right. It means your neutral that will be on extreme left. Your first winding, first phase, that will be A, B, C and N. You could see here the example is shown here basically. Your N that will be on extreme left and terminals that will lettered alphabetically from left to right, basically from this side to this side. And on extreme left there will be N. You could see in this example. The letters which are assigned numbers to serve as subscript, basically the letters are assigned with numbers to serve as a subscript. You can consider one example. If suppose there are 4 terminals from phase A which is brought out, so the numbering that will start from right, A1, A2, A3, A4. So this A1 and A4, if suppose there may be more number of terminals, so whatever would be the first terminal and the last terminal, that will be considered as main terminals. So in this case, the main terminal will be your A1 and the A4, that will be your main terminal. When the A1 is positive with respect to A2, so at that time the A1, small a1, means we are talking about the terminals on LV side. So that A1 will be positive with respect to A2, that is the LV terminal. We are talking about LV terminal. And on the same time, if it is tertiary winding is available, so 3A1 that will be positive with respect to 3A2. Then basically we said that transformer can be connected, the primary can be connected in star, secondary can be connected in delta. So it is represented by a symbol. That symbol could be your YD. For instance, we are considering a star delta transformer. It means your primary is connected in star, secondary is connected in delta, symbol will become YD. So here just pay attention what exactly the YD is written, how the YD is written. Here the Y is written in capital letter and the D is written in lowercase basically. So this capital letter is indicating that it is HV terminals. Means HV terminal is connected in Y fashion. Till time we were talking about primary and secondary. Now what we are saying that the Y is, capital Y is indicating that it is HV terminal and Y is indicating it is connected in star. The small letter is indicating that it is your LV terminals and the D is indicating that the fashion is delta. The configuration of winding, the connections, the 3 phases which are connected, that is connected in delta fashion. So you could have a look here. The other thing what you will find out, okay, when there is star and delta, so there will be some time displacement, time phase displacement will be there, may or may not be there between HV and LV line EMF. So how that would be represented with this symbol? This is not indicating the phase displacement. It is indicating that yes, the one set of winding is connected in star, another set of winding is connected in delta, but what about a time phase displacement? So this time phase displacement can be expressed in degree or by clock method of angle designation. So let us talk about what is the clock method of angle designation. So basically you have seen the clock. In clock you are having one is hand terminal, you can say minute hand is there and there is hour hand. So we are going to consider two hands. One is hour hand and minute hand, that is going to be considered. So HV line phasor, that will be represented by minute hand. You have to keep this thing in mind, okay, in order to understand the phasor group which we are going to cover in this lecture. So basically the HV line phasor, that is considered as minute hand. So minute hand is going to represent HV line phasor, and this minute hand, that will be always set at 12 o'clock or 0 hour position. So these are rules, you can consider these are the rules which is applied. So minute hand, that will be always at 12 o'clock. You could see in this diagram 1 clock representation for YD11 is shown here. So you can see the HV line phasor, that is basically fixed at 12 o'clock or 0 o'clock. And how the LV line phasor will be represented? The LV line phasor will be represented by our hand. So we are talking about clock method of angle designation, by which we are going to represent what is the time phase displacement between HV and LV line EMF. Here the HV line phasor, that will be given by the minute hand, it will be fixed at 12 o'clock, and the LV line phasor, that will be represented by our hand. So basically in this figure you could see the things. Now suppose you are having two winding three-phase transformer. So in that case you could see in this example we have considered a YD11. So the first symbol, that is going to represent HV winding. The second symbol, that is here D, it is going to represent your LV winding, and the third symbol, that is basically representing the phase displacement between LV and HV line EMF. Okay, so the first symbol, that is HV winding, second LV, third one is your phase displacement between HV and LV line EMF. Whenever you come across such symbol YD11 or YD something else, so it means it is representing polyphase transformer. It is representing three-phase transformer. In case of single-phase transformer, we have not discussed anything like this. Okay, so in this case, because there is star connection is involved, delta connection is involved, it may be your inter-star connection or zigzag connection that is involved. That's why there may or there may not be phase displacement between HV and LV winding. So now we understood that what exactly these symbol is representing. So this is nothing, YD11 is nothing, but it is representing polyphase transformer or three-phase transformer, and the first letter, that will be in capital, so it is representing HV winding. The second terminal, it will be in a smaller case, so it is representing LV winding section, and the third, that is going to indicate the phase displacement between HV and LV. Now what about if there is three winding three-phase transformer? Three winding three-phase transformer. At that time, the symbol, what you could see here, the YD11, it will be not there. So okay, in this case, suppose you are having this one symbol D Y1 Y1. So what exactly it is going to indicate? So the first letter, as usual, HV winding connection, it is going to represent. The second letter is in small case and it is Y here. So we are not talking about fashion, but the second letter, that is going to represent here LV winding, and LV winding, that is connected in star. Then what 1 is indicating here? The 1 is here indicating secondary line EMF, that is at 1 o'clock. In 1 o'clock, the secondary line EMF is at 1 o'clock. Then the next Y, that is third letter, which is written in a smaller case, it is representing the tertiary winding connection, and 1, of course, it would be representing line EMF. That is basically the time phase displacement that would be given by this 1. So 1 means again it would be at 1 o'clock. So tertiary line EMF, that will be at 1 o'clock. You could see here in this particular diagram that in this clock diagram, basically at 1 o'clock, that was the phase displacement between the primary winding and your secondary winding, HV and LV, HV and tertiary. So that time phase displacement would be given there. So this 1, basically what it is indicating here, the 1 is indicating means there is displacement of 30 degree. 30 degree displacement would be there, and that displacement is minus 30 degree 1, minus 30 degree it is showing. If it is on 11, so it will be your plus 30 degree. So minus 30 degree means lagging, minus means lagging here. We could consider another example, Y0D1. So what exactly it is going to indicate? The first letter HV winding connection, the second letter LV winding connection. The 0 means your secondary line EMF, that is at 0. The first number is indicating the phase, this time phase displacement for HV and LV. Okay, then the third letter, the fourth letter in this case, you would say that is representing tertiary winding, and the 1 again, that tertiary line EMF is at 1 o'clock. So we all must know how we can read it. Okay, this is required. So here secondary, that is in a star with its line EMF in phase with HV line EMF. Tertiary winding of lowest EMF is in delta with its line EMF 30 degree lagging the HV line EMF, or you can say minus 30 degree. 1 means minus 30 degree. Then from these two examples, what we understood that these are three-phase transformer and it also have tertiary winding. Okay, it has tertiary winding. So for three-phase, three-winding transformer, we understood that the first letter pertains to the highest voltage winding. Highest voltage winding, whatever it will be, that will be HV winding basically, and that is connection basically. HV winding, whenever I am talking about HV winding, so here please refer it as HV winding connection we are particularly talking about. And the next two letters pertain to the other two winding connection in order of decreasing voltage. In order of decreasing voltage means what? The LV winding, it will be when you are comparing with HV, so it will be lower than that. Whatever winding will be having lower voltage, that will be called as the LV winding, and the lowest voltage, that will be called as your tertiary winding. So in this way you can identify basically the windings in transformer. The last two letters are associated with clock hour number of the corresponding 0 hour position. Now let us talk about the phasor groups. So basically there are 4 phasor groups available. One is called as group number 1, 2, 3 and 4. So 4 phasor groups are there. The group number 1, that basically talks about the 0 degree phase displacement. Here you could see the phase displacement between HV and LV, when it will be 0, when both are in same phase. HV phasor, HV line EMF, LV line EMF, they coincide at that time. The time phase displacement will be 0. That's why we are calling it as 0 degree phase displacement group. So in 0 degree phase displacement group, the hour hand and the minute hand, that will be at a 12 o'clock, right? I think the things are clear to you. On the similar basis, the group number 2, that you can get it 180 degree phase displacement. This is your group number 2. So your minute hand and your hour hand, or you can say HV line phasor and LV line phasor, they will be 180 degree. They will be at 180 degree. So you could see it is 180 degree there. Then the group number 3, which is called as the minus 30 degree phase displacement. In this diagram, it is given in this figure. So you could see that there is a displacement of 30 degree. And group number 4, it will be of plus 30 degree phase displacement. So there are 4 groups which are representing 0 degree, 180 degree, plus 30 degree and minus 30 degree phase displacement. Now these groups, that will depends upon types of connection. What is the type of connection, whether it is star star, star delta, delta star, star zigzag, whatever it is. Okay, so in that fashion it is going to depend on, and the phase angle between HV and LV line EMF. So what you could understand, what we can conclude here, that each group characterize different phase displacement, that you can basically understand. So in order to understand these groups, some things you need to keep it in your mind. Some important points are there. So the phasor diagram, in phasor diagram you have to keep it in mind that phasor rotates in counterclockwise position. You know the clockwise position. So what would be the counterclockwise position? So the phasor is going to rotate in counterclockwise direction. You should keep that point into your mind. The phasor representing the induced EMF in the HV and LV winding for a particular phase are drawn parallel to each other. What it means, if suppose you are having a winding, phase A winding, so it will be having your phasor A1, A2, that will be your LV phasor. The small letters are indicating LV terminals, are, you can say, LV phasor. The capital letters, they are indicating your HV phasor. So it should be drawn parallelly basically. The A1, A2, that will be drawn parallel to capital A1 and capital A2. Here there is an assumption that HV winding is assumed to be primary and LV winding is assumed as a secondary. What we are going to discuss in that. So position, the next one is position of HV terminals A2, B2, C2 is assumed fixed. Keep this thing in mind when we are going to discuss group number 1. We are going to utilize these points. These you could say the rules are facts. You can consider in that way. So position of HV terminals A2, B2, C2 is assumed fixed. And how it will be assumed? It will be, we are going to consider one equilateral triangle. So at the top there will be A2, at the bottom right there will be B2, and on bottom left corner there will be C2. So think about an equilateral triangle. In equilateral triangle, position of HV terminal, that will be fixed. A2, that will be top. On bottom right, what would be your B2, and on left corner it will be C2. So according to this we are going to draw the phasors. Okay, so let us begin with group number 1. So it's group number 1. It is indicating 0 degree phase displacement. So what it means, that your LV and HV phasor, that is on same phase and displacement is 0. So clock hour diagram, that will be given by this one. Okay, so minute hand and hour hand, that will be at 12 o'clock. Now we are going to talk about Y/0 arrangement in order to understand the group number 1. Here Y means your HV is connected in delta or star. Y is indicating star. So your HV is connected in star. Small y is there. Second letter is in a small. It is representing your LV. So LV is also connected in star. The 0 is indicating 0 displacement. I think it is quite clear. Y/0. So no one is going to tell you the capital Y, small y, 0. He will tell you, okay, the transformer is connected in Y/0 fashion. So it should come into your mind that first letter will be capital, means first is indicating your HV winding. Okay, I think this thing is clear to you. For this particular group, the phase displacement between HV and LV line EMF, that will be 0 for this group. So considering the important points what we discussed, we can draw its phasor. So the phasor can be obtained like in an equilateral triangle. Already we said that A2 will be at the top and your B2 that will be at the right and C2 that will be on the left. So considering that its position are the fixed. So what you can draw? You can draw the other terminals. So other terminals, what it could be for HV phasor, it will be A1, B1 and C1. Why we are drawing it here? Because it is your star connection. So A2, A1, B2, B1 and C2, C1, that will be drawn in this way. And when you are going to draw the phasor for LV, so what you have to draw, it has to be drawn parallelly. Already we said, we assume that, or we considered that while drawing the phasor, what we have to draw, once A1, A2 is drawn, so you can draw A1, A2 for LV phasor. Then the B1, B2 or B2, B1 you could say that will be drawn parallel to this B1, B2. Then C2, C1 that will should be drawn parallel to this C2, C1. If suppose this C2 of LV that has to coincide with C2 of HV, then what you could see, it would be seen that LV line phasor C2 B2 has to, it must overlap the HV line phasor, because you are interested in getting 0 degree phase displacement. Okay, it means there will be no phase displacement, so it must overlap, which B2 C2 of LV side, it should overlap with B2 C2 on HV side. Considering this phasor diagram, you can make the connection diagram. You can show here the winding. So for HV windings, it is shown here in this connection diagram. You could use either connection diagram, there is not an issue. In a different way, the connection diagrams are shown here. So here neutral is also marked. So this is your star point A1, B1 and C1. So from here you can plot out one neutral connection, and similarly you can plot out a neutral connection for LV side, because both the windings are connected in star-star fashion. So there may be neutral exist, there may be no current in neutral, or there may be current in neutral. So we have shown here neutral as well. So I think it can be drawn easily considering this phasor diagram. This phasor diagram is drawn on the basis of the assumptions or conditions what we have seen earlier. So this is about your group number 1, 0 degree phase displacement for YY0 arrangement. We can consider another example, that is DD0 arrangement, delta delta 0 arrangement. So delta delta 0, so in this case we have seen the previous case for YY0. Considering that, you can draw a phasor diagram for this one. Otherwise you can keep the position same. So alternatively this diagram can be obtained. So here A2, see the assumption is the same, A2 that will be at the top. Okay, A2 has to be the top, B2 that has to be at the corner, your right corner, and C2 it has to be on left corner. So condition is the same. You could see here this is drawn considering this diagram, and here you can alternatively, it can be, because you can maintain the reference position as per our condition. So it can be drawn. Once it is drawn, that's fine, you can draw it here. So what attention or what thing you have to keep it in mind, okay, this is a triangle, it's quite good, but the later what you are going to mark here, that can give you the marks from university examination point of view. Okay, so what you have to keep it in mind, that letters, whatever you are writing here, you cannot write any letters at any place. So it is as per rule. So once it is obtained, this is for your HV side, this is for your LV side. Here only for HV side the phasor was shown here. So this is your connection diagram. Considering this, you could draw the connection diagram, I think, and alternatively you can draw this diagram. So in order to get delta, you could see, you can follow this diagram in order to obtain this. The three windings are shown there. So the three windings are drawn. Then which terminal is connected with which terminal? You could see that A1 and B2 are connected together. So what they have done, A1 and B2 are shorted by this wire, you could say. And then you could see here the B1 and C2 is shorted. So B1 and C2 is shorted by a wire. And A2 and C1, that is also shorted. So A2 and C1 is shorted by this wire. So in this way you got the connection. Okay, here all the connections, all the terminals are shown. You can say A1, A2, B1, B2, C1, C2, that is representing the three different winding, and these are the terminals basically you could see here, which is brought out from here. The another possible arrangement under group number 1, that it could be DZ0. DZ0 means what? Delta, zigzag or interstar. Interstar, not only star. Okay. And 0, that is showing the phase displacement. So its phasor can be drawn considering like previous case we have drawn it. So delta, there is no change in the phasor. Now what about the LV phasor? The LV is connected in zigzag fashion. So LV phasor you could see here in this diagram. Okay, so in order to obtain neutral point, what we need to do, we have to connect terminal A2, B2 and C2 together to form the neutral. And when we will join C1 with A3, A1 with B3 and B1 with C3, so we can obtain zigzag fashion. You could see it is shown in the zigzag manner, basically A3, A4. Here your C3 is connected with B1, C3 is connected with B1, and so on. So basically you will get this zigzag fashion diagram. So in this again there will be no phase displacement between HV and LV. Once it is drawn, you can draw this diagram, connection diagram. Okay, so this is your particularly what I call it as phasor diagram for delta, zigzag, zero phase displacement transformer are group number 1. Now there is a particular question about this particular arrangement DZ0. So why or when to use this particular connection? We are having delta delta, we are having star star, then why we should go for DZ0? You might have come across one thing in transformer, that is the harmonics. The third harmonics that is basically prominent in case of transformer. So we are always interested to minimize unwanted things. What is unwanted? That is harmonics. Harmonics need to be suppressed always. So whenever you are going with zigzag connection, so this allow you to suppress third harmonics EMF between line and neutral. So resultant third harmonics EMF between line and neutral, that will be basically 0. When zigzag connections are used, there is an important point which you could remember relevant to zigzag connection. The phase voltage or line voltage in case of zigzag is only 0.886 of its value in star. So this phase value would be 0.886. Inter-star connection that are used in rectifier circuit, star connection are not preferred in rectifier circuit. Now inter-star connection, why it is used in rectifier circuit, that could be one question. So the possible reason for it is a magnetic effect produced by direct current in each hop of the secondary cancels each other. It means you can say consequently, therefore core flux or core losses and temperature rise, that is unaffected. That's why inter-star connection is preferred or used in rectifier circuit. If secondary is in star with this we said na, star connection cannot be connected, it is not used. But if it is there, so what would happen? So the DC current would divide equally in three phases. The direct current that will be divided into three phases. Flux is going to produce by this current, which will be added to the alternating flux. Thereby it is going to increase core flux, core loss, and of course temperature rise will be there. So in order to avoid the temperature rise, we know that we use insulation in transformer on the basis of temperature. If it exceeds, so what would happen? The insulation, if temperature is exceeding a predetermined level, so your insulation, it may get damaged. It may get damaged, maybe there is melting is possible. So what would happen? There is short circuit between the windings. So if short circuit between winding is there, so ultimately it will be burned. Possibly it may burn, or there is short circuit, so it will be considered as a fault. So in order to avoid that, the secondary is not connected in star when you are using a rectifier circuit. It is preferable, or it is suggested to use inter-star connection DZ0, and it is also suppressing your harmonics. It can be used wherever the quantum of harmonics requirement is quite low. At that time you can consider the DZ0 transformer.